Okay. Welcome to the Colloquium and the Dean Lytle lecture. This is the second of the lectures. Professor Vincent gave the first lecture yesterday. And I would like to introduce Professor Vincent, who is Dean of the School of Engineering and Applied Science at Princeton University. And he is also the Michael Henry Strater University Professor of Electrical Engineering. Before joining Princeton, he spent 13 years at UIUC. Dr. Poor is a member of the National Academy of Engineering, a fellow of the American Academy of Arts and Science, and a former Guggenheim Fellow. He is a fellow of IEEE, former president of IEEE Information Theory Society, and a former editor-in-chief of the IEEE Transactions on Information Theory. And he received the 2005 IEEE Education Medal and 2007 IEEE Marconi Prize Paper Award. I went to the Amazon.com. I typed his name, and I found 12 books, both from introductory text to advanced text, with recent books on wireless network multi-user detection in cross-layer design, and also quickest detection to be published in November 2008. So he's a distinguished scientist and educator. And we are happy to have him.
Thank you very much. Thank you very much. Good morning. Again, let me just express my appreciation to the Lytle committee for inviting me to give these inaugural lectures. It's really a great honor. And I really appreciate particularly Les Atlas and Louis Scharf for inviting me here and making all these wonderful arrangements. It's been a great day and a half so far. This is, as Louis, if you were in my lecture last night, you know that this is my inaccessible lecture. I gave 2 lectures, one accessible, that was yesterday, so if you missed the accessible one, too bad. This one is the inaccessible one, which I think means it's the more technical one. But hopefully it won't be that inaccessible. I'll try to make this one accessible as well. So the theme of today's lecture is, as you see, competition and collaboration in wireless networks. And essentially what I'm going to talk about is what I see as the sort of recent trend in wireless networking research toward looking more broadly at interactions among nodes in a network rather than looking only specifically at what happens between 2 nodes, between pairs of nodes, between a pair of nodes. So to set that up, let me just give a little bit of background on my view of where research in the field of wireless has been and where it sort of is today. And then I'll go off on a couple of particular themes in this direction. So, just looking back 25 years to what is the beginning of the current wireless, the development of current wireless networks. Of course, wireless is a very old technology going back to the 19th century. But, the current interest in wireless really began mostly in the 1980s with the development of cellular telephony. And there have been a lot of sort of physical layer or link level developments in that time. CDMA and OFDM, code division, multiple access, and orthogonal frequency division multiplexing were not invented in the last 25 years. These go back further, but certainly they've come into their heyday in that period of time. CDMA through the standards up to and including the 3G standard, the standards in OFDM, which is the main physical layer for most 4G systems. And then also there have been some other rather important developments in the physical layer, multi-user detection, which combines with CDMA to provide more efficient use of spectrum when you have interference channels. MIMO, multiple antenna systems, of course, was sort of shocked the world in the 1990s by showing that you could that fading, which we always thought was a bad thing, is actually a good thing that can be exploited to give us increased diversity or increased capacity. And then finally, turbo processing primarily through the development of turbo codes and turbo decoding. Again, sort of shocked the world of communications in the 90s by showing that you could decode very close. You could design codes that could be decoded practically and achieve very close to Shannon bounds. So, these are very, particularly these last two, have really revolutionized the systems that we use today. And certainly almost any new standard has some elements of MIMO in it, and many have elements of turbo codes and so forth and other turbo type processing. So these are major things. Each one of these, I listed these particular ones because each one of them was sort of a watershed in the development of the wireless systems that we have today. And of course there's a lot of, I'm not writing the obituary of this work, there's a ton of interesting stuff going on in this area, and there's much great research and much more to be done. But I just want to point out that this has really been the centerpiece of what happened in wireless over the last couple of decades. More recently, we've seen an increased focus on interactions among nodes rather than sort of link level things. That is just two link level things. I'm talking about what happens transmitting data from one node to another. Here I'm thinking about looking at interactions among nodes as groups. And I'll just point out some perhaps familiar research themes that we've seen in recent years that would indicate this. And I've grouped these into two kinds of interactions, which is sort of the theme of my talk here. One is competition. And I'll just, some competitive type things that we see in current research in wireless. One example is cognitive radio, right, where you have a primary user and then you have secondary users who are looking for opportunities to jump into holes in the spectrum and make use of those. So that's a competitive situation among the secondary users. And in some ways it's competitive between the secondary users and the primary users. Another theme of a lot of research just in the last few years has been in physical layer security. That is taking, I mentioned MIMO, which has allowed us to exploit the physical layer for greater capacity and reliability, taking the same ideas and try to exploit the physical layer for security rather than using higher layer security techniques like encryption. Take advantage of the inherent randomness of the physical layer to get security. This is a competitive, I put this under the category of competition because security is naturally a competitive situation. You have an eavesdropper who wants to eavesdrop on your communications and you don't want them to. And then finally, there's been a lot of work on game theoretic modeling, analysis, and design. And this, of course, is game theory is a sort of generally a way of looking at competitive situations. It came up mainly through economics. And so this is one of the themes that I'm going to talk about in more depth today. Now, in collaboration, we've also seen a lot of interesting work. I mean, one of the things that we read a lot, almost every other paper these days has the word cooperative in it. Cooperative transmission and relaying, there's been a tremendous amount of work in this area. Also where this is a situation where different nodes in one way or the other help each other to get greater capacity. In some ways, this is just a natural extension of MIMO to more distributed type systems. Another area where collaboration is important is in multi-hop transmission and ad hoc networking, where you no longer, as a node, you're no longer mainly dealing with an access point, but you're rather dealing with all your fellow terminals and everyone's trying to get their data through the network by helping one another in a multi-hop fashion. A couple of other things, distributed beamforming. This is another type of collaborative technique where single antenna nodes can work together to do beamforming. And then collaborative inference, which is primarily of interest in sensor networks where nodes work together to make inferences about the environment. And this is the other topic that I'm going to talk about primarily today. So I've sort of divided these in addition to thinking of competition, it's being kind of an economorphic way of looking at networks. That is, it's like, economic systems are typically modeled as competitive systems. Game theory, as I said, sort of arose from these kind of models for economies. And this is a very useful way to think about competition in networks, is to think about them as being economic systems. So I call it economorphic networking. Collaboration, on the other hand, is more what I would call sociomorphic networking. That is, it's people working together to either accomplish a common goal or to help each other accomplish their individual goals. I'll say a bit more about this later. So in this sort of general context, I want to talk about, in particular, these two items. That is sort of game theoretic modeling of networks and collaborative inference. So I'll spend about half the rest of the time on each one of those. So here's the particular things I'm going to talk about. First of all, I'll spend some time talking about energy games. And this is a way of modeling the energy efficiency of wireless networks using game theory. And we can think about this as being a model for competition in communication networks. And then the other problem, as I mentioned, will be distributed inference. And here, this is an example of collaboration in sensor networks. So the distinction being that communication networks are networks for which the application is communication of data or communication of voice. And sensor networks are networks in which the application is primarily inference, detection, and estimation. So let me start out by then talking about energy games and as a sort of paradigm for competition in communication networks. And this is what I'm going to talk about now is mostly joint work with one of my former PhD students, Farhad Meshkati, who's at Qualcomm now, and Stu Schwartz, one of my colleagues at Princeton, and a few other people whose names I'll call during the course of the discussion. So let me now go back to this theme of economorphic networking to start this section off. So the idea here is that we view the nodes in a network as economic agents, just like economists like to look at us as being economic agents. And each one is seeking to maximize its own utility. So utility for us is always measured as some kind of happiness or dollars or something like that. For nodes in the communication network, we would measure utility as sort of energy efficiency or spectral efficiency or something like that. And so some examples are non-cooperative games where nodes compete for radio resources. And the examples I'm going to talk about are of that variety. But there's some other ways of using this view to examine the behavior and even design communication networks. You can think about auction-type behavior, auctioning behavior, bidding by nodes for services. Or coalition games where you have repeated games that the way a node plays a game on one instantiation of the game incentivizes or de-incentivizes that node to do things on the next, rewards or incentivizes nodes to do things on subsequent plays of the game. So this might come up, for example, in multi-hop transmission. So what this view gives us is, first of all, new ways of understanding network behavior. We'll also see in the examples I'm going to give that it gives us some new design tools, new ways of actually making design choices in networks. It's also based on individualized node behavior. That is, it looks at nodes as individuals, just like economists look at us as individuals. And I'm going to look at this in the context of what I call energy games, which I'll switch to now. So this is what I mean by an energy game. And here I'm going to look at a multiple access network because this is the easiest way to look at this problem. And so think about an infrastructure network. It looks like we've lost the right-hand side here. I don't know if there's anything we can do about that. Well, hopefully there won't be anything important over there. If there is, I'll tell you. Because I can see it all on this screen, so it's not a problem. I have a tendency to use the whole canvas here when I put these together. So basically, we'll look at an infrastructure network where there's an access point and a number of terminals. We're looking at the uplink, so we have a number of terminals communicating up to the access point in a multiple access channel. So basically, these users are competing for resources because it's a multiple access channel. So whatever actions one user takes affects those of the other users by interfering with them. So we can think about this as a competitive game or a non-cooperative game. And here we'll look at this where the payoff is measured in bits per joule. Okay, so energy efficiency. How many bits can I get across the link per joule of battery energy? And here's a formalism for this problem, which was devised by a number of people at Rutgers in WinLab, David Goodman, this is Narayan Mandayam, Roy Yates, and others there. And the setup is the following. You can model, for this setup, you can model a game with k players, where the players are just the terminals. Each terminal, the kth terminal, has a set of strategies, which we call A sub k for that terminal. These are strategies it can use to play the game. And UK is a utility function for terminal k. So it's the payoff that terminal k gets when it plays the game. And the utility function of interest here, as I said, is energy efficiency. And that can be measured for the kth user as the ratio of the throughput over the link to the transmit power used to get that data across the link. And that throughput, of course, is measured in bits per second, and transmit power is measured in watts or joules per second. So the units of this are bits per joule. So this is what we want. Now, how can we model this? We can look at it a little bit more carefully. The transmit power is a straightforward quantity. But the throughput, we have to model a little more carefully to make this problem tractable. So we can model it in the following way. The throughput for user k we can model as the transmission rate for user k times the frame success rate of user k. So you think about an ARQ system where frames are being transmitted across. When they're successful, all that data goes through. When they're not, they have to be retransmitted. This is really the good put, so-called good put of the link. And we can more particularly model the frame success rate as a function f, which is sometimes called the efficiency function, of the received signal to interference plus noise ratio of user k's signal after signal processing. So gamma sub k is the SINR with which receiver k's signals are received after signal processing but before data detection. So this is a good model for frame success rate, and many types of physical layers satisfy this model. So typical additive white Gaussian noise channel with QPSK, for example. These kinds of models all have this kind of a functional form. And the nice thing about this model is that it abstracts the physical layer, that is the actual noise, fading, and all that stuff, and modulation choices and receiver choices, into this function f. So we can think about more generally about what's happening among the nodes without worrying too much about all the details of the physical layer. So it encapsulates the physical layer. Now you can see why this is a competitive type situation, because the transmit power of a given user is going to appear in the numerator of its own SINR, and it's going to appear in the denominator of all the other users' SINRs. So when if I'm a user, I turn up my transmit power, I'm going to increase my own SINR, which is hopefully going to be good for my frame success rate, but I'm going to decrease everyone else's, which is going to be bad for theirs. So there's a competition going on. So this is really a game in SINR when it gets down to this formalism. Now, Farad and Stu and I took off on this theme and studied the following uplink game, where we fix a linear receiver at the uplink. This is here I mean a multi-user receiver. It's a multi-access channel. So this is something like a minimum mean squared error receiver, say. And then each user will select its transmit power to maximize its own utility. So the idea here is that the set of actions for a given user is to turn the power up and down on the transmitter. So here's a theorem that this is joint work with Narayan Mandayam, actually. which is several years old now, but it says that if f is a sigmoidal function, now we're getting off the edge, I'm sorry, a sigmoidal function, meaning that it's S-shaped, so a sigmoidal function is just one that for which there's a point to the right of which it's concave and to the left of which it's convex, and it's also continuous and increasing and goes through 0. It's a sigmoid. Then for any time, if any time this efficiency function is sigmoidal, which turns out to cover most of the cases of practical interest, we have a Nash equilibrium in this game. That is, it's a point at which no user can unilaterally improve its own utility, so-called Nash equilibrium. And this equilibrium is reached when each user chooses a transmit power that achieves a particular target SINR gamma star, which is a solution to a simple nonlinear scalar equation. F, again, is the efficiency function that determines the frame success rate. F prime is just the derivative. So this is a simple nonlinear equation. Gamma star is a function of the physical layer. But beyond that, all you need to know is that what you want to do is to have the terminals achieve SINR balancing, and then you've got a Nash equilibrium. So this is an interesting problem in its own right. And from game theory, first of all, this Nash equilibrium is unique. There's some nice iterative algorithms you can derive for it. But here I want to talk about its value as an analytical tool for measuring network performance in terms of energy efficiency. And particularly, once we have the Nash equilibrium, that tells us something about the optimal equilibrium energy efficiency achievable in the network. So we can start looking at the effects of various design choices on the Nash equilibrium value, the energy efficiency at the equilibrium. And in particular, I want to look first at the effect of receiver choice on the Nash equilibrium. And I'll look at three particular linear receivers. The match filter, which is sort of the classical receiver against white Gaussian noise when you don't have interference. The decorrelator, which is a zero forcing receiver, which is sort of the classical receiver against interference without additive white Gaussian noise. And the minimum mean squared error detector, which is a trade-off between those two. That is, it actually tries to balance mitigation of interference and noise. So just in the example, I'll look at a flat fading single input multi-output model where we have each terminal has a single transmit antenna, and the access point has an array of P antennas. I think that's the picture I showed had that on it. And then each path is a flat fading path. That is, every path between transmit and receive antenna has a channel gain associated with it, but it's not frequency selective. You can extend this to frequency selective, but just this example is not frequency selective. And so this shows the Nash equilibrium for a particular example, which I'll describe now. So the model here is now random CDMA, so random code division multiple access, spread spectrum, where again we have K terminals and the spreading gain is N. That means each symbol, if you will, is multiplied up by a bandwidth expansion factor of N by multiplying by a high rate signal. And then, so the load of such a system is K over N, the number of terminals divided by the spreading gain. That's the number of users per dimension in this system. So it's a measure of spectral efficiency. And then I want to look at the large system limit. That is, let the K and N go to infinity with alpha fixed. So we fix the load, but we let the spreading gain go off to infinity. And when we do that, it turns out that we can use random matrix results to show that the SINR in this limit is not stochastic anymore. That is, it's a constant. It doesn't depend on the specific instantiations of the spreading codes. So that just allows us to more easily examine what happens at equilibrium. And then, so for that situation, what I've shown here on both of these charts, but let me pull up the one on the left first. I hope you can see the green. This is the utility, that is energy efficiency, versus load, that is spectral efficiency, at Nash equilibrium for these three receivers in this model. The green is for the match filter, the blue is for the decorrelator, and the red is for the MMSE detector or receiver. And then the two lines for each one of these receivers correspond to 1 and 2 receive antennas respectively. So in the first case, it's a SISO channel. The second case, it's a SIMO channel with 2 receive antennas. And so one thing you note, first of all, is that energy efficiency and spectral efficiency are opposing criteria. As the spectral efficiency goes up, that is, as alpha gets larger, the energy efficiency at equilibrium goes down for all of these receivers. Another thing you notice is that the match filter is not very good, except when the load is very small. And that's because it's just mitigating the ambient noise. It's not doing anything about interference. And these loads, by the way, are sort of the loads that are supported by match filters in cellular systems. So these are kind of practical loads for existing systems. But if you want to go to higher loads, you need to use one of these other receivers, both of which do reasonably well with one antenna. But the stark difference is when you add a second antenna at the receiver, then you can see that the MMSE detector greatly outperforms generally the decorrelator even, and certainly the matched filter. So a message here is that the receiver signal processing can make a big difference in the energy efficiency at the terminals. So this receiver processing is being done at the access point. So we're not so worried about energy consumption there. That's plugged into the wall. We are worried about energy consumption at the terminals, which are battery operated typically. And you can see that we can do a lot for energy efficiency by using the right receiver at the access point. And for example, if you look here at 60% load, moderately high load, but not the highest loads we can support here, you can see that just going from the decorrelator to the MMSE detector, which essentially have exactly the same computational complexity, we can double the energy efficiency at the terminals. So there's something to learn here from this analysis. Now on the right, this shows just the MMSE detector. Again, utility versus load for the MMSE detector, and this just shows the effects of adding more antennas. So green is 1 antenna, blue here is 2 antennas, red is 4, and black is 8 antennas. And I'll point out that this is now a logarithmic scale on the vertical scale axis, whereas over here it was linear. And so you can see that basically when you double the number of antennas, you sort of double the energy efficiency. Roughly there's a sort of a linear relationship between the number of antennas at the access point and the energy efficiency at the terminals, the mobile terminals. And this is actually analytically, if you look, you can analytically determine, in this large system limit, you can analytically write down the equilibrium energy efficiency or utility, and you can see this linear behavior. So this is a little bit like another result we know about multiple antenna systems, which is that the spectral efficiency increases more or less linearly with the number of antennas. That's the famous result of Foschini and Gans in one of the early MIMO papers in the 90s. Okay, so the message here is that this is a really good tool and one that's fairly tractable for looking at the behavior of energy efficiency in such networks. So now one question you might ask is, well, if we have an access point, why don't we just let the access point tell the terminals what powers to transmit at to optimize overall utility, that is, do what's called a socially optimal thing. So one model for social optimality is the so-called Pareto optimality, where the idea is that rather than selfishly choosing your own power so that you don't change your own, in the Nash equilibrium, you don't change your power because it doesn't do you any good. Okay, that's the sort of Nash view of equilibrium. In the Pareto view, you don't change your own transmit power because it might hurt someone else. That is, a Pareto solution is one where an equilibrium is one where no user's utility can be improved without decreasing someone else's. Okay. Now, it turns out that unlike the Nash equilibrium, Pareto solution is generally very hard to find. It has to be done numerically. It's true that the Nash equilibrium is generally not Pareto optimal, as you might guess, but it's actually very close, and it's provably close for some of these receivers I just looked at. So if we go back to the same example as before, but with just one receive antenna, this shows, again, utility versus load for the match filter, again in blue, very light here is green. This is the decorrelator, and red is, again, the MMSE detector. And the two lines for each one of these correspond to the Nash equilibrium is solid, shown in solid line, and the Pareto solution is shown in a sort of a dashed dot line. And you can see that there's very little difference in any of these receivers between the Pareto and the Nash equilibrium, except when you get to very low utilities. And for the decorrelator, in fact, they're the same. For the MMSE detector, you can show analytically that they're very close to one another. And for the match filter, again, this is not really a very good design choice anyway, but you can see that even for the match filter, until you get low utility, the Nash equilibrium is really achieving very close to the Pareto solution. And the nice thing about the Nash equilibrium is that it's decentralized. That is, each terminal is making its own decisions. So let me just introduce one other wrinkle here, and that is, in most wireless systems, quality of service is important. That is, different media being transmitted across the wireless link require different kinds of service. So, for example, delay is a major thing, as is rate for many media. So we can model this by adding a queuing model to the terminal. So here's the terminals that we had before. If it weren't off the side, there was an access point over here. At each terminal now maintains a queue of packets, which we assume are coming in at Poisson with some rate. They're FIFO'd at that is the first in, first out queues. The packets are sent across the links using ARQ, that is acknowledge repeat requests. If they get through, fine. If not, a NAT comes back and they have to be sent again. And the QoS is measured here in terms of source rate and average delay. So we already looked sort of at, so this is how we're going to measure quality of service, the rate at which packets come in and the average delay it takes to get them to get across to the access point over here. And it turns out that in this model, this putting a bound on these parameters, or putting bounds on these parameters, translates into putting a lower bound on SINR. So that means that when we're playing the game, we're playing a constrained game. We can't just allow any SINR. We've got to at least have a certain minimal SINR for a terminal to achieve its QoS requirements. We can also enlarge the set of actions where not only can the terminal choose its transmit power, but can also choose its transmit rate, or bandwidth, the amount of bandwidth it's going to choose to use. Okay, so now we have a game with two actions, and it's a constrained game. Now, it turns out that this problem doesn't universally have a Nash equilibrium, but it does always have a Nash equilibrium if the quality of service constraints and the bandwidth and so forth satisfy a certain inequality. And that inequality is achieved by assigning to each of these users a quantity of size, which I don't have the analytical expression for here, but it's an analytical expression for what's called the size of a user. It depends on the QoS parameters, the bandwidth of the channel, and so forth. And the size is a number between 0 and 1. As long as the total number of sizes of all the users trying to access the channel is less than 1, you have a Nash equilibrium, which is something like an SIR balancing equilibrium. And so this means that in addition to using the game, you have to have some kind of access control. That is, the MAC, the medium access layer, has to control the number of users that can enter the network and play the game. Okay? But once that happens, then you can achieve Nash equilibrium. And then in that, again, you can get that in closed form. it allows you to analyze what the effects of QoS are on energy efficiency. And here I've just got one simple example. This again is a random CDMA. This is with match filter receivers. And this shows again the utility. This is normalized. Just look at the shape, don't worry about the numbers, versus delay, again normalized to bandwidth. And you can see that as this is the delay requirement here. You can see that as the delay requirement tightens, that is, as we go to the left here on the x-axis, the utility dies. So as long as you have a loose delay-tolerant traffic, you can get, delay doesn't affect energy efficiency much, or delay constraint doesn't. But as you tighten the delay, what happens is you have to transmit with higher power to make sure that your packets get through quickly, and that causes more interference. It means you have to transmit even higher power per bit, and then per bit per second per hertz, and that means that you then get very low efficiency. So delay, quality of service can cost you if it's too stringent. Now, rates quality of service also is shown here. There are three source rate QoS parameters. The first one in blue is when we need 1,000th of the total bandwidth of the channel for the source. This is when we need 100th, the black one, and the red one is when we need 1/10 of the bandwidth. And you can see that for very light bandwidth requirements, again, there's not much effect on energy efficiency, but if we start needing a significant amount of the channel's resources, well, energy efficiency is going to drop. Okay. So again, this is a tool that allows us to analyze the effects of these parameters on the network performance in terms of energy efficiency. So there are a lot more things of interest in this area, but I want to move on to the other problem I want to talk about. So let me just mention very briefly a couple of other results. There's some other results on receiver design. I showed these results on choosing linear receivers. We can also look at nonlinear multi-user receivers like maximum likelihood or maximum a posteriori probability or interference cancelers, all kinds of, there are all kinds of nonlinear multi-user receivers. And if we look at the large system limit for random CDMA, we can also find Nash equilibria for receivers using those nonlinear algorithms. And interestingly, what we find here is that by going from the MMSE detector, which is the most efficient linear receiver, to the maximum likelihood detector, say, which is the gold standard of multi-user detectors, you don't gain a lot in energy efficiency, although you do gain a lot in complexity. The multi-user detectors, the nonlinear ones, tend to be very complex. So it turns out that it doesn't always pay to use nonlinear. If you're just worried about energy efficiency, it doesn't always pay to use nonlinear receivers, unlike spectral efficiency, where you get a lot for nonlinear reception. We've also looked at equalization when you have rich scatter, so you don't have a flat channel. In the ultra-wideband systems, the scatter is, meaning the multipath is very long, has a very long tail. And you can also analyze this asymptotically by doing some large random matrix theory and get some nice closed form results there. These papers both appeared earlier this year. We can also look at the modulator. This is receiver design. So you can look at choice of different equalizers, I should say, and the effects on energy efficiency. We can also look at modulation choices. So we can look at choice of carrier in the multi-carrier case. We can look at the choice of modulation index in the just more generally, that is, if you use, say, quadrature amplitude modulation, how many constellation points do you want to pack in? And we can look at the choice of spreading waveform if you want to use spread spectrum. And the message of all of these works, they're all quite different, but sort of a very overarching message is that what you do for energy efficiency is sort of contrary to what you would have done for spectral efficiency. That is, for example, multi-carrier, to get spectral efficiency, you use water filling across all the carriers. To get energy efficiency, you choose one good carrier and use that only. Modulation index, to get spectral efficiency, you use the highest order modulation you can support. For energy efficiency, you use the lowest order modulation that allows you to achieve your QoS, and so forth. So it's kind of interesting to see that if you choose energy efficiency as design criteria, and you do different things than if you choose spectral efficiency. And this formalism allows you to do that analytically. Also, I mentioned relay auctions. One way to do auctioning is to, in systems with relays, to allow terminals to auction, to bid for the services of a relay. Okay? So that allows you to efficiently make use of the relay and for the value of the relay to be priced in the network. You can also look at, I mentioned before, multi-hop systems. You can use repeated games to incentivize terminals to forward traffic of other terminals, which is a problem if you have a network that requires multi-hop transmission. It's a problem for the nodes on the edge of the network because they can't, there's no quid pro quo for them. They can't forward other people's packets. So you can solve this problem, or at least address this problem, by using what's called coalition games. And that's to appear soon in the transaction zone communications. So now let me shift gears and talk about this other problem, a problem that involves more collaboration. And this is joint work with another one of my former PhD students, Joel Pred, who's now at the RAND Corporation, and my colleague Sanj Kulkarni, and some other people whose names I'll call. So first of all, let me look at the counterpoint to economorphic networking, which I call sociomorphic networking. Here the idea is that nodes work together. And we can think of two modes for this. One is collaboration, where nodes are working together on a common goal. And the other is cooperation, where nodes are working together, help each other to achieve their individual goals. So a cooperative communication system is an example of the second one, and I'm going to give an example here of the first one. So now the idea is that the value of this view of networking in terms of, for engineers, is that it leads to new algorithms and new protocols for the way nodes interact with one another. Sort of contrary to the economorphic view, it's based on collective behavior of nodes rather than nodes behaving as individuals. And again, here I'm going to look at this problem of distributed or collaborative inference in sensor networks. So just let me say a little bit about why sensor networks are sort of fit into this framework, whereas communication networks may not. But first of all, here are some of the main features of sensor networks, particularly wireless sensor networks. And first of all, the main application of sensor networks is inference, detection, estimation, and mapping. Okay, there's the main, for communication networks, you might have application might be web browsing, email, what have you. This is always about inference, sensor networks. So it's a common goal typically. Also, another salient feature of sensor networks is that information at different terminals is often correlated. So in a communication network, say in a cell phone network, my conversation is not going to be correlated with yours typically, or my emails are not going to be correlated with yours in a data network. But in a sensor network, because sensors are sensing a physical phenomenon, if the sensors are close together, they're likely to have similar measurements or correlated measurements. Another salient property of wireless sensor networks is that energy is often severely limited. And of course, in all wireless networks, energy is always limited, okay? But in say, a cellular network where you have your cell phone with you, you can recharge it at night, right? But a basic idea of sensor networks is you put sensors in places where people don't go. So it's hard to charge the batteries. It's hard to change the batteries. So energy is a more serious issue in sensor networks than it is in other wireless networks. And again, this sort of plays into this first one, is that typically in a sensor network, the nodes have a common goal. The nodes in a sensor network aren't in it for themselves. They're in it for the goal of the sensor network, to detect seismic events or whatever it might be doing. So this really leads to a collaborative setting, and where sensors are going to work together to make inferences, transmit data, or what have you, and usually with the goal of conserving resources as much as possible. So I'm going to look again at, in this context, at collaborative inference. So as a model, you can think about a situation where sensors are distributed at random in some area, start collecting data, and they're wireless, they transmit to one another. And I'm going to look particularly at the problem of learning. There are other inferential problems we could look at, but I want to look specifically at learning here. So this is just a little background tutorial on learning. I think many of you, this is superfluous, but here's a setup of what's called supervised learning. We have an input space, or think of this as an observation space, which is here d-dimensional vectors. We call observations x. And there's an output space y, or sometimes called a target space, or inference space. And the idea is here we observe x, and y is some quantity we'd like to predict from x, or to estimate from x, or detect from x. Okay? So x and y, a pair of observations and a target or output, is just a random variable that has some joint distribution, p sub x, y. And a design here is a mapping from the observations to the outputs that predicts the outputs from the inputs. So it's an inference machine. And we'd like to design such an F to minimize some kind of expected loss. For example, it could be probability of error, but here I'm going to look at minimum mean squared error. So we'd like to minimize the mean squared error between the prediction of y, which is some function of x, and y itself, the true value. So the idea is we see x and we don't see y. Now, if this joint distribution is known, of course, this is just classical statistical, Bayesian statistical inference, that we know the answer here is the conditional mean of y given x. But what if we don't know x, the joint distribution of x and y, which certainly in a sensor network application would be something we would expect, because the sensors are out there, we don't know where they are, we don't know what kind of environment they're in, so we just don't know the joint distribution. So learning theory tells us how to construct optimal estimators F from examples. Okay, so we take a set of examples of observations paired with the true inferences, the correct inferences. We use those, and if we have enough of them, we can construct the optimal F, even though we don't know the joint distribution of x and y. So it's the samples are a surrogate for knowing the distribution. Okay, so what does this have to do with sensor networks? Well, so now let's think about a situation where we have a sensor network, and we can think of this as being a distributed sampling device with a wireless interface. So these sensors are out there, they're taking data. Maybe they each have their own exemplar or some set of the exemplars that they're measuring themselves. And they can communicate wirelessly in some way. So there's a spatial relationship, and that's going to define a topology or a graph, if you will, that'll shape how collaboration can go on among these terminals, because it's cheaper in terms of resources to communicate with your neighbors than it is to communicate all the way across the network. Okay, so this sort of defines a collaborative topology. So now, first of all, one way that we could deal with this problem is to for each sensor to send its exemplar off to some centralized processor somewhere. And then the centralized processor could then take all the exemplars and try to learn the field, say, that we're trying to estimate with these sensors. So we let F denote that field. Y is so F is a function of the x's. Here the x's might be positions or some other things, temperatures. And we want to do a least squares fit of those exemplars. Choose a function F that does that. And one way that this can be done well, and which is well known from literature, is to use so-called reproducing kernel Hilbert space methods, where we restrict the function F to lie in a set of functions called a reproducing kernel Hilbert space, which is just a set of functions with certain smoothness properties. And we can fit the fit the function within that set subject to a penalty constraint on the norm of the function. So this is just to keep the function from being too wild. And this is I'm not going to go into this, is a very standard classical way of doing function fitting in this kind of setting. And this, if n goes to infinity, the number of sensors, this consistency results you can get here with the conditional mean and so forth. But the problem is that to solve this classically, all the data has to be transmitted to a common point. And the idea here is that we'd like to conserve energy and bandwidth at these terminals, so we don't want them to be transmitting data off to some common access point. So we'd like to do something a little bit more in a more distributed fashion. So that means we could think about the sensor I as measuring some subset of these exemplars, and then accessing its neighbors to somehow exchange data. Okay, that is, local sensors can talk to each other about what they've seen, but sensors are not going to be able to communicate with all of the other sensors in the network. Okay, and the justification for this is that it's efficient to communicate over short distances because the diffusion losses are small, but if you want to communicate over long distances, you're going to have large diffusion losses and shadowing and other things. So this sort of motivates a model of this sort, where we think about having learning agents. In our case, these are the sensors, and say we have M of those. And we have training examples, a database of training examples, N of those. These are the exemplars I mentioned before. And then we can organize the relationships between the training database and the learning agents in terms of a bipartite graph, where one set of vertices contains the exemplars, and the other set of vertices contains the learning agents, and there are edges between vertices whenever a learning agent can access a particular datum. So you might think about these lines as in that previous picture as representing connections to nearby sensors in the network. Okay? But this is actually a very general model. We can model centralized learning with in this same model. That is, we have one learning agent and we have n data points, and they all are accessed by the centralized processor. The model we have is sort of spatio-temporal field estimation. The data is distributed among the sensors, and then each sensor, which is a learning agent, can access nearby sensors' data by efficient local communication. So that's sort of the model that we have here. But there are other models. For example, we could have a public database. That is, there could be a published set of data, which is common, and then each learning agent has its own set of data. So in a sensor network, this could be broadcast from some central point, for example. But more generally, we've got this general model. So what can we do with it? And think about this as an abstraction of the sensor network with where we'd like to do distributed processing. So one natural approach here is to use local learning. That is, just to go to the problem I mentioned before, the RKHS fitting problem, and to let each learning agent just do RKHS fitting using its own data. That is, the data it has access to. So it's just apply the same problem, but each learning agent has access only to certain data points. Local learning. A problem with local learning is that it's incoherent, typically. That is, for example, in this picture, this learning agent 1 and learning agent M share this data point. But they don't share all the data points, so they're going to make different inferences about what this function should be, f, and it may have different values on the same observations x. So this is called incoherence. And you can show that if you do local training only or local learning only, you can wind up with incoherence. And incoherence is provably bad. That is, you can show that there's a theorem that says that if you have incoherence, there's always a better estimate that's coherent using the same structure. So the question we might ask is whether the sensors can collaborate in some way rather than just reading each other's data, maybe they can exchange information in some way locally that allows them to get the optimality of coherence while retaining the efficiency of locality. And the answer, of course, is yes, otherwise I wouldn't have brought up the question. And maybe I'll just very briefly, how much time do I have, by the way? 5 minutes. Okay, let me just briefly go through this. So essentially, we can think about doing local learning. This is just a local learner at sensor S. But after we do local learning, we update the database with our inferences. That is, we don't just leave the database untouched. We make our own inferences based on our local learning, what we know from multiple data points that we can see. Then we go and update all those with our inferences. And then you go to the next sensor, and the next sensor does that. So you iterate through sensors, doing this one at a time, local learning, updating of the database. And then, in order that this thing doesn't just go wild on us, we add an inertia term. This just penalizes the norm of the next iteration minus the previous iteration, essentially. And if you put it all together, you get basically an iterative algorithm like this, which is going to appear in the, actually this is to appear in the information theory transactions, which basically looks something like this. You choose the kernel, you estimate initially, you do your initial estimates, then you iterate through through time, you iterate through sensors, and at each sensor, and each time at each sensor, you do a curve fit. Then you update all of the database to which you have access to, and then you go to the next sensor. It happens again. You go through all the sensors. Then you go through time. Okay. It actually looks more complicated than it is, but essentially it's a message passing algorithm. That is, we have a bipartite graph. It's low density. So this may suggest LDPC decoding to you. It's the same kind of algorithm. And the sensors or the learning agents do their thing. They update the database by passing messages back down to this set of vertices. And then another sensor does the same thing, and we move across. And then the next time we do it again. We keep iterating. So as we're iterating, we're passing messages down and updating the database. But still, all the communication is local. There's still no global communication going on here. It turns out that this algorithm converges to a relaxation of the centralized RKHS estimate to the topology of the graph. It's locally coherent. We don't have coherence. It's also very simple because it's actually just a parameter estimation problem. It's not a function estimating problem or a functional estimating problem. It's monotone. And if we have certain connectivity assumptions on the graph, and have IID exemplars and so forth, it converges to the conditional mean, okay, which is the global optimum. So it has a lot of nice properties. I'll just show a couple of examples and then I'll wrap up. Here's two examples, one where the target function is linear and one where it's sinusoidal. The sensors are placed on a line, drawn at random uniformly. The topology is described in terms of simple distance between sensors. And what we'll look at is just the fitting area for this algorithm versus the radius of neighborhoods. So just go back here, a neighborhood is defined by all sensors that are within a certain radius R are in the same neighborhood. So R is a parameter. And here we can look at these two examples. This is the linear target, and this is a sinusoidal target for, this is test error, meaning mean squared error, versus the radius of the neighborhoods for three algorithms, centralized, which doesn't depend on the radius, local only, which is this top one, and then the algorithm I just described, which is this one, message passing. You can see that for relatively small neighborhoods, you get basically the same performance as centralized processing with only local communication. The other one is a little wilder, but it's basically the same message. That is, the local-only performance is quite poor. This is centralized. This is a simulation, so it's a little edgy, a little ragged. And then this is the message passing algorithm. Let me mention very briefly a couple of other things, and then I'm done. We can also look at other issues of distributed learning in other topologies. For example, one where the sensors only communicate with an access point, but communicate with only single-bit messages. So they use their resources to communicate one bit back to the access point. Here you can show, under certain conditions, consistency in learning, even with a very simple model like this. Another problem of interest is beamforming. That is, rather than making inferences, let the sensors get together to collaborate to form a beam on the access point, and then since their data is correlated, they can, create a common message and form a beam on the access point and save energy that way. So it's another way of collaborating to save energy. And then finally, I'll just mention a related problem, which is called judgment aggregation. The problem of making incoherent judgments coherent is called judgment aggregation in the social science literature. And this is a problem that comes up in psychology and politics and so forth. And Joel and Sanj and I have worked with Dan Osherson, who's a psychologist at Princeton, on sort of general efficient algorithms for judgment aggregation, which is going to appear in decision analysis. There's an 08 here. It's going to appear later this year. That's interesting. We're actually doing an experiment right now where we're doing judgment aggregation on judgments about the upcoming presidential election. So we have a survey that people take to make predictions about what's going to happen in various states in the current presidential election. If anybody's interested, I'm happy to send you the link to get you to take the survey. And we've got about 7,000 or 8,000 responses already. We've advertised this on various political websites. And at the end, we're going to take all these judgments, which are going to be incoherent, believe me, and try to apply these algorithms to it to see how well we can predict the outcome of the election. So with that, let me just summarize. Looked at two things here. First of all, a general setting where we think about examining communication networks in terms of node interactions, sort of abstracting what happens down in the physical layer to making that abstract so we can look at what happens at higher layers. We looked at two modes of interactions: competition, which is suitable for communication networks, and collaboration, which is suitable for sensor networks and other types of networks. And the two particular problems we looked at were energy games, where we saw that Nash equilibrium provides a nice analytical tool for examining issues of energy efficiency. And in the case of distributed inference, we saw that there's this, we can think about, once we establish a model for distributed inference using a bipartite graph model, a sparse bipartite graph model, we can then start looking at algorithms, developing algorithms and studying them for this kind of inference. And in particular, we looked at this message passing algorithm, which has a lot of nice asymptotic properties. And with that, I think I'll stop and take questions. Thank you. Yes.
So I understand that the Nash equilibrium is a nice analytic tool, but in practice, suppose you have something that doesn't achieve the equilibrium. Would you actually deploy it?
Yeah, well, that's a very interesting question. I mean, it is primarily an analytical tool more than the design aspect of it, more than designing the algorithm, is designing the. It gives you a way of getting a handle on sort of the net energy efficiency of the network. So then you can start saying, well, I want to use one of these receivers. Which one am I going to use? It also gives you algorithms. There's some papers and so forth on algorithms, but whether those are the ones you want to use in practice or not may not be true. It's really more gives you guidance as to what to do to make the system more energy efficient. So it's a very good point. It's a subtle distinction. It could be a design tool for the algorithms themselves. I mean, certainly you can design those, but it may be a little bit too abstract. Just like Nash equilibrium in an economic system is really an abstraction, right? I mean, there's all kinds of things that happen in real economies that don't satisfy that kind of utilitarian selfish model. So I think I like to think of it as really more of a tool for designing the externals, not the algorithm itself. Yeah. That's a good question, though. That's an excellent question. So we looked at, okay, we haven't looked exactly at that problem, which is a nice, interesting research question. That is, how much do you save? But one thing we did look at is how much do you save by using message passing over centralized processing, by simply sending the data back to the datum back to the access point, and then you don't have to iterate, right? Now, if you iterate only once, there's a clear savings because you're only doing local communication. But as you iterate more and more, the cost of local communication starts piling up, right? So if you go here, you can see that as connectivity increases, the mean squared error gets better, right? But also as the connectivity increases, the amount of energy expended on collaboration goes up. So you can model that. I don't have any graphs here, but you can sort of look at various algorithms, various growth rates for connectivity, and you can see that some algorithms save you energy by message passing and some don't relative to centralized processing. So it's not a clear win. It's still a design that has to be done here, because the assumption that local processing is always better than global processing is not even always true. But I mean, there are situations where it's definitely a win. Now, one thing we haven't looked at is multi-hop. That is, start passing through you might start passing data through the network somehow. And if it's fully connected, that's going to work. It may not, the results I showed you don't require it to be fully connected, though. So, I mean, there are situations where you may not be able to do full multi-hop and so forth. So, I mean, there's a lot more here to do. This is not a fully completed area of study. So that's a good area to look at. Yeah. Here's one here. Yeah. Hi.
Instead of using Nash formula, what if I just the same utility function definition, but I use some kind of like optimization theory, like a minimax or those kind of theory? Most likely, I can still achieve the distributed control and try to achieve the common goal compared to using this equilibrium theory. What do you think?
Well, I mean, minimax, definitely is something that you could do. I mean, the thing about minimax is usually, in minimax you have one criterion, and some users are trying to minimize it and some are trying to maximize it, right? Or nature is trying to maximize it and you're trying to minimize it, or something like that. So here, the difference is that each user has its own individual criterion to maximize, and no one else is really trying to minimize it. It's not really that kind of a zero-sum game. It really does, I think, fit more of a Nash game type model. Not that there aren't other ways of applying minimax here. This particular formalism, I don't see how minimax would work. But certainly, I'm sure there are other ways of injecting minimax. And of course, in other problems of receiver design, minimax is very powerful, like robustness, for example, and things like that.
Okay, I think that we should thank our speaker and thank you all for turning out.
Thank you.